Okay, perfect. So here we are, and welcome everybody. Thanks for attending live this FDH presentation. And today we will have Alessio Testa from University of Chieti. Well, he is an earthquake geologist. He got his PhD in 2023, and he works mainly in seismic and fault displacement hazard assessment applied to critical facilities and sites. And today he will present his work on a strategic dam, and the title is PFDHA, an application for distributed faulting for a strategic dam in central Italy. So Alessio, the floor is yours. You will have 30 minutes, 40, what it is, it's fine. And at the end, we will have a Q&A session. And as usual, the recording will be in a few days on the Fall2SHA YouTube channel.
Okay. Thank you, Francesca. I don't know if you can see my screen.
Yes, perfect.
Maybe yes, okay. Hi, everyone. As Francesca said, I'm Alessio Testa. I'm a postdoc fellow at the University of Chieti, Italy, in the Department of Engineering and Geology. And I'm also the co-founder of Shaking, which is a spin-off of the same university, which works mainly in seismic hazard and fault displacement hazard of strategic and critical infrastructures, such as dam. And today I'm going to show you an application of PFDHA for a dam in central Italy, starting from the gathering of the data needed for the model to the PFDHA application. So I'm going to start with a brief introduction about the fault displacement hazard and the approaches to fault displacement hazard, and then to the case study and the geological background of the area of study. Then I'm going to show you the fault characterization about the Monte d'Oglio fault concerning the principal faulting hazard, and about the Anghiari fault concerning distributed faulting hazard. And then I will show you the results of the PFDHA analysis. So, as you know, everyone here knows that fault displacement hazard is a localized source of hazard due to the occurrence of slip during a strong earthquake, of course, along an active incapable fault, and that we talk about primary faulting when the rupture occurs along the trace of the main fault, and we talk about distributed or secondary rupturing when the ruptures occur far from the main fault, at a certain distance from the main fault. The approaches to fault displacement hazard are usually two. The first one is the so-called zoning and avoidance approach, which actually consists in the definition of a respect zone around the fault, and this approach doesn't give numerical results about the hazard, and it is mostly used in the land planning, for example, in the Italian seismic microzonation. The second approach on which I will focus today is the probabilistic fault displacement hazard analysis, which, as you certainly know, gives the probability of exceedance of a certain level of displacement in a certain site, which can be the infrastructure site, for both primary and distributed faulting, and starting from empirical relations, empirical models, which are usually based on the observation of surface rupture of historical earthquakes. The results are expressed in terms of hazard and curves, hazard curves and maps. The main goals are critical facilities, emergency buildings, lifelines, and also risk-based intervention strategies. The case study, so the studied infrastructure is the Monte d'Oglio Dam, which is located in the northeastern sector of the San Sepolcro Basin. in the northern Apennines of Italy. The San Sepolcro Basin is part of the Upper Tiber Valley. It is a northwest-southeast oriented extensional basin bounded by normal faults. The main fault is the Anghiari Città di Castello fault, which is made of two different faults, the Anghiari fault to the north, and the Città di Castello fault to the south. And we have also an antithetic fault on the other side, it is called the San Sepolcro fault. And the northern edge of the basin is actually featured by an high angle fault, which is mostly actually is orthogonal to the main faults. The basin is actually undergoing active extension with the stretching direction oriented nearly orthogonal to the normal faults. In the Upper Tiber Valley, 7 damaging earthquakes occurred during the last 700 years, with magnitude ranging from 5 to 6.3. But unfortunately, most of them are poorly constrained by macroseismic data, as you can see here. According to the recent Italian regulations, if a dam is located in a high seismic area, a seismotectonic study must be carried out in order to define the ground shaking seismic action and also for fault displacement hazard purposes. And these guidelines recommend to start the study from existing national scale database, such as the Ithaca database. The Ithaca database summarizes the information on potential capable fault on the whole Italian peninsula. And it is a compilation database. So in general, it is not suitable for site-specific studies. As you can see here, across the dam, the database shows a potential capable fault, which is called the Lake Montedoglio fault. It is mapped as a secondary fault. It has a length of 6 kilometers. So in case of surface faulting, it could have an impact similar to primary faulting for the dam. Anyway, the quality of the studies in the literature, according to the database, is low. So the capability of the fault must be demonstrated. Okay. In general, in the San Sepolcro Basin, there are no numerical constraints on the fault activity at the time of the study. But just some geomorphologic inference were published in the past. The Montedoglio Dam is shown here on the right. It is an earth-filled dam with an height of 60 meters and a length of 570 meters. And it is a strategic dam according for the Italian law, because it is used for potable water and in irrigation purposes. So this is our map, our geological map of the area of the dam and west of it. And in dark blue, you can see the old pre-quaternary bedrock deformed by the compressional tectonics during the Miocene. And from yellow to orange to light blue, there are the continental deposits accumulated in the San Sepolcro Basin during the Quaternary. So the first target of this study was to understand if there is a long capable fault beneath the dam. Actually, we did not find evidence, we did not find evidence of a single continuous fault crossing the dam. Instead, we mapped several parallel faults in the bedrock that we called the Montedoglio fault system. One of those faults crops out here, and it strikes through the dam, actually. Those faults should intercept the continental deposits in this area. So we acquired some geophysics, 2 seismic reflection lines here and here, high resolution seismic reflection. One of the line is also calibrated thanks to boreholes. And in one of the boreholes, we also collected a sample for OSL dating. And we also dated some other samples of alluvial deposits. From the seismic lines, you can see that we observed no evidence of faulting of the young deposits, of the quaternary deposits, and there are no evidence of young activity of the fault, such as abrupt steps in the bottom, at the top of the bedrock. So the Montedoglio fault system seems to be formed by old faults confined within the bedrock and seared by alluvial sediments older than 56 kilo years, as we know from the OSL dating. We also performed some GPR and trenches in this area here, close to the dam on a fluvial terrace of the Tiber River. And in the trench, we observed that the faults are within the bedrock and are sealed by 4,000 kilo years alluvial deposits. So the conclusion of this part of the study was that there is no evidence for considering the Montedoglio fault as a capable fault. There is no evidence for considering principal faulting hazard at the site of the dam. But anyway, the dam is very close to the main fault of the basin. Here you can see two of the splays of the main fault, which is the Anghiari fault. Here you can see the Micciano splay and here the Motina splay. Which are at a distance of 1.5 to 2.3 kilometers from the dam. So it is not possible to exclude secondary faulting at the site of the dam, especially since we have a pre-existing discontinuity here, which is actually one of the display of the Montedoglio fault system. So we decided to perform a PFDHA analysis in order to evaluate the hazard from secondary faults. And so we started studying the Anghiari fault, for which there were no constraints about the activity in the literature. And therefore, we performed some geological survey, producing this map, for example, and some quantitative geomorphology, geophysics, and paleoseismology. And this fault, as you can see, bounds the eastern side of the Anghiari Ridge, which is made of Pleistocene gravel exhumed by the fault activity. The fault has a segmented geometry, being made of 4 different fault sections, the Anghiari Motina section and the Fighile section running at the base of the hill, and also the Micciano and Valcelle section located uphill. I'm gonna focus mostly on the Anghiari Motina and Micciano section, which are the closer to the fault. So we acquired DSM from satellite images at the scale of the whole basin, and we focused on the Anghiari Ridge, performing a morphological analysis. This is our morphological interpretation. We mapped several features such as paleosurfaces, triangular facets, fault scarps, alluvial fan, and so on. In particular, we mapped 2 different kind of surfaces. You see the surfaces mapped in orange are continuous and elongated, while the surfaces mapped in green, located on the eastern side of the ridge, are small and discontinuous. And so in order to understand the different origin of the surfaces, and in order to understand if there are if these surfaces can be used as marker for the slip rate and displacement evaluation of the fault, we made several point cloud SWOT profiles parallel and perpendicular to the faults, projecting the points of the DSM within a certain buffer on a line. So this is the parallel to the ridge profile. On the bottom, you see the geomorphological interpretation. Actually, we mapped the same feature that I showed you in map U. And here you can see that the surfaces on the top of the ridge are dipping towards southeast, likely if they are related to the Tiber River, while the surfaces mapped in green are small, discontinuous, incised by gullies, and also bounded by fault scarps. Looking at the perpendicular to the ridge profiles, you see also that the surfaces on the top are tilted towards southwest, while the surfaces mapped in green are dipping toward northeast, likely if they are related to the gullies that are incising the eastern side of the ridge nowadays. So our hypothesis is that starting from this initial configuration, the Anghiari fault caused the exhumation of the ridge. Then a new established southwest northeast directed flow caused the carving of a cut terrace that has been then displaced by the continuous fault activity of the Anghiari fault, and finally incised by the gullies. So if our hypotheses were confirmed, it would mean that these surfaces could be used as a marker for the long-term displacement and slip rate of the Anghiari fault. But what we need is the age of this surface. Here are just few pictures just to show you how these surfaces looks like. On the top left, you can see surfaces located at different elevation and bounded by the fault scarp. On the bottom left, you can see that these surfaces are actually cut surface, so erosional surfaces. And on the right, you can see two surfaces bounded by the fault, a perched valley, and the gullies that are incising the ridge. So to verify our hypothesis, we improved the detail of our analysis, acquiring a DTM in the area where most of the surfaces are located. And we mapped the same feature with an increased details. Then we selected two sites, one in the hanging wall and one in the footwall, to try to date the surface using the cosmogenic nuclide method. These are just the results of the chlorine-36 analysis. As you can see, there are some problem. For example, for the site at the hanging wall, there are just few samples. For the site at the footwall, we don't have the upper part of the curve, so maybe there is further erosion here. Anyway, considering 2 meters of erosion at the footwall site, we obtain very similar ages, 40 plus minus 9 kiloyears for the footwall site, and 42 plus or minus 9 kiloyears for the hanging wall site. So it seems that our hypothesis is supported, but we have large uncertainties and assumptions. So then to constrain the vertical displacement and slip rate of the fault, we projected the risers of these paleosurfaces and the gullies on the main direction of the gullies. So as you can see here, the vertical displacement ranges from 20 to 43 meters, which is also comparable with the value of incision. And so we get, using the ages that we constrained thanks to the cosmogenic nuclide dating, we obtained a throw rate ranging from 0.39 to 1.39 millimeters per year. Anyway, since we have large uncertainties, we decided to use only the slip rate from paleoseismology to constrain let's say, as input for the model. Concerning the geophysics and paleoseismology, we selected 3 sites across the Anghiari-Motina section and Micciano section. The site 1, where we also acquired some geophysics, where the fault is very clear, as you can see here in the seismic reflection, but also here in the georadar. The site 2, which is actually the Podere Todari site, where we found an outcrop of the fault on a road cut. And finally, the site number 3, located on the scarp at the base of the ridge. This is the site number 1 in Villa Sterpeto, where we dug a 50-meter long trench. The main feature of this trench is, of course, the fault zone here, which separates the Pleistocene gravel in the footwall from a colluvial unit, which has an age of at least 25 kiloyears in the hanging wall. This is the log of the fault zone. As you can see, we have several stacked colluvial wedges, and each wedge is located above a fine-grained dark deposit which look like weak paleosol. So we interpreted these paleosols like earthquake horizon. So We interpreted each wage as a colluvial wage due to a surface faulting event. And we collected sample for radiocarbon dating, and we constrained at least 5 surface faulting earthquakes in the last 25 kilo years. Concerning the site number 2, we have a more distributed fault zone affecting the Pleistocene gravel, but also a Paleostrine to colluvial sequence, which has an age of 7 kilo years. We have several evidence of surface faulting earthquakes, such as colluvial waves and an open fissure. So we dated 3 surface faulting earthquakes in the last 7 kilo years, the most recent of which has an age which is comparable with the 4058 magnitude 5.8 historical earthquake occurred in the San Sepolcro Basin. This is the last paleoseismological site located at the base of the ridge here, the Anghiari Trench. The trench was 50 meters long. This is just the log of the fault zone. We can see 3 faults here, but the most important spot is this one, where we can see the fault. It's quite subtle, the trace, but we can see here some colluvial waves displaced by the fault. We don't have very strong time constraint in this case, but we can see 1 or 2 surface faulting earthquakes occurred between 3,000 years ago and the 14th century, according to radiocarbon dating and some pottery shards that we found in the colluvium. So, as I said, we don't have very strong time constraints, but these earthquakes seems to be comparable with those we found in the second site. So at the end, we rebuilt the seismic history of the Anghiari Fault, constraining the age of at least 7 surface faulting earthquakes in the last 25 kilo years. We have 2 different hypotheses, one in red, one in blue, for the last 2 earthquakes, because 2 of the samples has incongruous ages, but anyway, we don't know which one is the favorite, but in one case we have some clustering here, and in one case we have a more constant slip rate, but the younger earthquakes are actually the same. These data are published in Tectonics in 2023, and we also constrained a slip rate of 0.14 to 0.35 millimeters per year, which is actually close to the lower boundary of the slip rate that we constrained with the cosmogenic nuclide dating. So at the end, we got the fault parameters we need for the modeling. So we have the fault geometry and segmentation. We know that the fault is located at 1.5 to 2.3 kilometers from the fault, depending on which segment is considered as principal faulting. And also we know that the dam is located in the hanging wall of the fault, in the, let's say, in the location where most of the distributed faulting are usually located, according to this figure from Visini et al. 2025. So concerning the methodology, at the time of our study, the only work assessing fault displacement hazard in a probabilistic way for normal faulting environment was Young's et al. 2003. Particularly the earthquake approach. It has the same components of the PSHA, and this is the general equation by Young's. The annual rate of exceedance of a specific value of displacement in a certain site is given by 2 terms, which are the fault activity rates and the displacement attenuation function. The last is also given by 2 different terms, one for the conditional probability of occurrence of slip, and one for the distribution of the slip along the fault, or at distance from the fault, if we are talking about distributed faulting. So basically, first we have to determine the earthquake rates on capable fault. So assessing all the fault parameters, fault geometry, and so on. Then for each earthquake magnitude on the fault, we have to compute the probability of having surface faulting. using, for example, empirical regression by faulting style. Then for the earthquakes producing surface faulting, we have to estimate the displacement on the principal fault. But if the site is at a distance, a certain distance from the principal faulting, we have to determine the hazard from distributed faulting. So first we have to estimate the probability of having distributed faulting, which are function of the magnitude, the style of faulting, the distance from the principal fault, and the location in the hanging wall or in the footwall. And then we have to determine the displacement model, let's say, the amount of displacement at increasing distance from the principal fault in the footwall and in the hanging wall. Again, it is function of the position on the respect to the hanging wall or the footwall, but also as a function of the distance from the principal fault. And finally, the results are given as hazard curves with an annual rate of exceedance of a specific value of displacement. Concerning the specific case study of the Monte Toglio Dam, after getting all the fault parameter, since the fault system is segmented, we decided to explore 4 different fault rupture scenarios. Each surface rupture scenarios imply different rupture length, different earthquake magnitude, different displacement on the principal fault, and different distance from the principal fault for the dam. The minimum distance is 1.5 kilometer, and the maximum distance is 2.3 kilometer. The magnitude range from 6.3 to 6.6. And the worst scenario is the scenario number 4 in terms of magnitude. The activity rates and maximum magnitude were computed using the FISH codes by Pace et al. 2006. We also implemented the method by Young's with the curves of probability of occurrence of distributed faulting published by Ferrario and Livio 2021. As they are constrained by a wider and updated database of normal faulting surface ruptures. The authors proposed 2 different curves, the regular and the conservative curves, and we decided to use both of these curves. Here you can see several hazard curves for the site of the Monte Toglio Dam, showing the annual frequencies of exceedance of a certain value of displacement. The different colors are the different rupture scenarios from black to red, and the different line pattern are the different equation that we used. So Young's without any implementation, Young's implemented with the Ferrario regular curve, and Young implemented with the Ferrario conservative curve. Ferrario and Livio, sorry. I put here some reference exceeding probability, which are actually the reference used for ground shaking in the Italian regulations. Because we don't have in Italy any information about reference return period for surface faulting hazard. As you can see, all the curves are below these references used for ground motion. Then we obtained the mean curve with the error, and because since we don't have any indication in the Italian regulation for the surface faulting, I put here as reference the annual frequency of exceedance used in the PFDHA study for the Yucca Mountain Nuclear Waste Repository, which are 10 to the minus 4 and 10 to the minus 5, which are into 10,000 years and 100,000 years. The mean curve never intercept even the 10 to the minus 5 line. Only the upper percentile intercept this curve, and it means that we expect the displacement value less than 1 centimeter with a return periods of 100,000 years. So the hazard level is actually quite low. And the engineers and geologists of the Office of the Ministry in charge of the safety of the dam in Italy judged this level of risk acceptable, and the final result was continue operating. The results of this analysis were published in 2024 in Engineering Geology, for who is interested in see the details. So some conclusions and perspective. The PFDHA is a method of great potential for faults that cannot be avoided by infrastructure, or fault discovered after the construction of the infrastructure, or even if there are new stricter regulation, such as for the Monte Doglio Dam. It is also useful to account for both principal and distributed faulting, for both the occurrence and displacement estimation, and it also helps risk-based decision on and actions actually. Very high detailed geological investigation are needed because precise principal fault location is very important. And also what is important is the fault style, the position of the infrastructure respect to the fault, and all the fault parameters. One of the key parameter is the slip rate, of course. And so quantitative earthquake geology and geomorphological survey on high resolution dam is very recommended. And it is also recommended to dig several trenches in different sites to estimate the slip rate. And about issues and perspective, especially about distributed faulting, the current regression do not account for near surface geology, and it would be good to have specific regression for different type of near surface lithology. And also implementing the PFDHA methods with more regression for distributed faulting could be useful. For example, in order to consider the presence of pre-existing discontinuities, for example, what recently Vicini et al. Published. And also further empirical studies are needed. So such as update the database available, such as FDHI and SURE database. And also it is needed to study, to have new physics-based modeling. So that's all from my side, and thank you for the attention.
Thank you, Alessio. Very, very clear, and also very clear the reasoning and the implications. So we now have plenty of time for questions. So please, from the audience, you can unmute yourself or type into the chat.
Hello, can I ask you a question?
Yeah,
yes.
I'm here.
Hi. Great. Thanks a lot for the talk. Very, very nice talk. Very well structured. I would like to ask the following. What about this distributed faulting scenario? For a magnitude 6 earthquake, okay, 6.3 perhaps or 6.6, the most, I think the let's say the worst scenario, or even for a 6 point, let's say this amount of magnitude, okay, 6.5. How is it possible to assume that distributed faulting will occur 1 kilometer away from the primary fault? Is there any place in the world that you have, from literature, someone mapped the primary tectonic features 1 kilometer away from the fault that ruptured with a 6.5 earthquake? I mean, I'm referring to the physics here, not to the modeling.
Yeah, I understand the question.
Yeah.
Actually, yeah. One example is this one, no? The figure I showed you, no? Here you have 18 earthquakes between 5.6 and 7.5, with several secondary rupture up to 8 kilometers, but even more if we are considering also sympathetic rupture, triggered rupture on sympathetic faults. So yeah, I would say yes, there are examples in the literature. Now I cannot answer.
Yeah.
I mean.
Okay. Yeah, yes, yeah. I know what you mean. Perhaps when you have really large earthquakes like the 2023 East Anatolian fault earthquakes, where there were some ruptures, maybe a few hundred meters away from the main fault.
Yeah, but I think it depends a lot on the fault style. These are only normal faulting earthquakes. For example, in the 2016 earthquake in central Italy, there were a lot of rupture at very far from the main fault. Even triggered rupture in another basin, actually on another fault. So I would say yes for it, and it was a 6.5 earthquake. So
yeah.
Okay. Yeah. I hope I answered your question.
I accept the answer. I have to look at myself because I was surprised. I have to dig more carefully to the literature. Yeah.
Okay.
Because I was expecting a few hundred meters, not 1.5 kilometer. I have another question. Why? What material did you use to date with cosmogenic isotopes? There was a surface there. If I recall the maps, was it an alluvial fan was displaced?
Yeah, actually, we collected. I show you in the picture. No, sorry. We dug a very small pit, as in the example here. You see here, and we collected pebbles from this gravel. Pebbles of limestone and sandstone in order to analyze both chlorine 36 and beryllium 10 along a depth profile. So what we obtained was the concentration with the depth, which allowed us to rebuild the curve of exposure to the cosmogenic rays. So the answer is pebbles of limestone and sandstone.
Okay, thank you.
You're welcome.
Okay, is there any other question from the audience? Okay, so I will add one for Alessio.
Okay.
So toward the end, you said there is no guideline from the regulatory side. So basically, the ministry decided based on ground shaking efforts. So do you think this is a problem much bigger than the geological side, or what's your impression?
Good question. I think let's say the ministry have no ideas actually. So this is the problem. And also this problem started to be addressed in Italy just a few years ago because, we don't have nuclear facilities, and this is a kind of study that is mostly related to nuclear facilities. So maybe in other countries they have a specific regulation, but we don't have. I think it is, let's say, politics problem more than a geologic problem. I don't know, but I don't think that is the case to use the same reference for ground shaking.
Yeah, that's my same idea. So I think there is an elephant in the room because we can improve our models and put more data and more data, but on the other side, we should be more effective into asking the regulatory side to provide clear guidelines or numbers at least.
Yeah, I agree.
Can I add another question?
Yeah, please.
Madam Chairwoman.
Sure, of course.
Yeah, because when you do such a detailed study, all right, they did GP ground penetrating radar, they did seismic, okay, everything they did, right? So I'm coming back to this question of distributed faulting. You could identify, doing all this work on the hanging wall of the main fault, right? The north-south one, the Anghieri, or so.
Yeah.
Well, you did all this work, and I don't think you actually identified any splays that could potentially move during the primary rupture and produce secondary ruptures. So that's why I'm skeptical about this method, because you assume that there's a chance of having distributed rupturing mainly on the hanging wall. But in fact, when you do the seismic surveys and everything else you do, right, you don't find any other inside the basin, any other splay faults. So maybe this distributed faulting actually is gravitationally induced from ground shaking and because of large accelerations than tectonic, maybe.
Okay, I have said more than an answer, let's say. First of all, as I said, actually, I go back to the map, one moment. Actually, we know that beneath the dam, there is a discontinuity, which is this fault here that crops out on the road to the dam. And we also know the presence of this fault from a picture from the building of the dam. It's very clear in the picture, the presence of a discontinuity, which is of course perpendicular to the main fault, but it is on the edge of the basin. So we cannot say that in case of the activation of the main fault, I think you can expect something here, no? First of all. The second thing is that, yes, you are right. This is one of the limitations of the Young's method, that they don't take into account the presence or not of pre-existing structure. They just account the distance from the main fault. That's why sorry for this slide. One moment. That's why I put in the perspective here the needing of more regression for distributed faulting, also accounting the activation of pre-existing faults. So we have to distinguish between random distributed rupture, which of course can be related to other phenomena such as shaking, from ruptures on pre-existing discontinuities that of course we see here in the site of the fault. But there is this very young study here, Vicini et al. 2025, if I remember well, is on earthquake spectra. They showed something similar. They account this kind of problem. And I forget the other answer that I was thinking about, but I hope I answered.
Yeah, don't worry. Okay, thanks.
You're welcome.
Francesca, I have a question.
Yeah, sure.
Alessio, can you go back to the hazard curve?
Yes. This one, the mean curve?
Yes.
Okay.
Yes. So you indicate the 10 centimeters as a kind of value not to exceed, but do you have an engineering constraint on that, or do you think that even 1 centimeter in a dam could be a problem?
Okay, so first of all, yeah, I put here 10 centimeters as an example. It is not a reference. It is not coming from my engineering observation. It is just to help people to read the curve. But anyway, I think it depends on the kind of dam. From my experience with other dams and talking with the engineers and dam owners, it depends on the kind of the dam. For example, as in this case for earth-filled dam, I don't think that 1 centimeter is a problem. But one of the engineer with which I talk about this, he said that 1 centimeter can be a problem for concrete dam. It can be a problem, even a very small displacement.
Okay. Thank you.
Welcome.
Well, since you asked this question, I want to add another thing which is an open question for me. So below that 10 centimeter, you see there is the plateau of the curve, basically. So almost flat part. So I think the PFDHA method could not distinguish between 1 and 10 centimeters. So maybe this is a critical point from the probabilistic point of view. So we can provide the curve, but the halfway for 1 or 10 centimeter is almost the same, and this could be quite critical from the applied engineering's perspective. So maybe that's something we could discuss more or explain more to the engineering side. That's at least my personal impression.
I agree, and sometimes engineers ask for exactly for this. No, they would like to know for very small amount of displacement. We try to explain that we don't have that much detail, even because the Young's method starts from they use a grid, which is very large actually. So we don't have that much detail, even for these reasons. I mean, so. Yeah, I agree with your sentence. We don't have this detail at very low displacement.
Okay, I think maybe Bruno wants to add something.
No, I only was thinking that I totally agree with you, and it's an important message what you said. We cannot improve our methods to have such details, but we have to communicate to engineers the limit of the approach. We can give a number, but it's a number that has no significance. So it's important what you said, Francesca. Is a message that we have to be careful to say to engineers.
I agree.
Okay, so if there are no other issues or comments, I thank again Alessio for the cool talk. And well, so far we don't have real plans for the future. We will wait for the summer, and then probably we will continue the thematic talks. So if you want to suggest speakers or topics, feel free to contact me. And well, the recording will be in a few days on YouTube. So keep in touch, and thanks everybody.
Thank you, Francesca, for inviting me.
Thank you, Francesca, and have a good summer, everybody.
Summer.
Thank you, Una.
Thank you, you too.
Thank you. Thank you.
Bye.
Bye.
Ciao.
Bye-bye.
Bye-bye.
Ciao. Bye.